our pillar of strength, our beloved, determined, and versatile principal, Mrs. Hina Falke ma'am, to welcome our honorable guest and take the program ahead. Hina
Thank
ma'am.
you, Loveleen ma'am. Thank you so much. A very good evening to all of you, the dignitaries present here. To begin with, I would say that stars will never won by little minds. We must have big minds as space. And I don't think the human race will survive the next 1,000 years unless we spread into space. With this, I would like to first welcome our very own CMD, Mr. Bipin Pote of Pote Group of Education. He's a very young, dynamic entrepreneur, and he has been working passionately for 17 years through 3 verticals. The 7 branches of Pote Tutorials, having more than 3,000 students spread all over Kalyan and Dombivli, Late Bhaurao Pote Vidyalaya, and the Cambria International School stand witness to the success. In his journey, he has been guiding and mentoring more than 20,000 students and 40,000 parents through his patience, resilience, commitment by grooming them to be confident. I request Bipin sir to share his views before we start the program. You're welcome, Bipin sir.
Thank you.
On behalf of the entire Cambria International.
Thank you, Hina madam.
Thank you.
Thank you. I hope I'm audible to all of you. So thank you, Hina madam and entire team. Thank you, Mr. George, for accepting our invitation. It's been a month. We were in a touch with you for this kind of event. So it's been a great pleasure to have you among us. So thank you to Mr. George, and thanks all the team and the entire parent and student who had joined this program. Yes, Mr. George, I had seen the vision of the NASA. I must say there is a line written over there. We bold the boundaries. We expand the boundaries in the air. It's one of the line I had liked very much, and it's truly amazing line. It's proven that still we are expanding the boundaries on air. So thank you for joining us, and my dear student and parent. I'm not going to much take off the maximum time because we are excited to hear Mr. George. And I must say this initiative we had taken, so our student should think, they should start thinking toward many things on this planet. And that's the reason we have initiated this event. So thank you for joining us. Yes, Mr. George, all the students are excited to hear you. So I'm not going to take much of the time. At the end, you are having already 2 questions. Out of that, I would love to ask 2 questions also, which I'll declare right now only. So I'll save the time of the presentation. The question is, I would love to hear about the Mars 30. NASA had recently launched Mars 30 VR program. So at the end of the presentation, if you throw some light on Mars 30 program, and I would love to, although I'm a big fan of Elon Musk, he is the CEO of SpaceX, and they are having a vision of the company to make this world living on multi-planet. So then also I am having a question, why NASA had partnered with SpaceX. So these are my 2 questions, which I'm excited to hear from you at the end after your presentation. So thank you for joining us, Mr. George and entire team of TCS and students and parents. So thank you.
I would now welcome our Managing Trustee of Cambria International School, Mrs. Meenal Pote, who is also the President of Innerville Club, Kalyan Riverside, who is also a great inspiration behind this program. You're welcome, Meenal Madam. Now, I take this opportunity to welcome our most awaited guest speaker today, Mr. George Salazar. Mr. George Salazar received his Bachelor's of Science in Electrical Engineering from the University of Houston and his Master's from Science in Systems Engineering from Southern Methodist University. He has over 35 years of experience in telemetry communications, speech control, command and data handling, audio displays and controls, intelligent lighting, project management, and systems engineering. He has been involved with the design of advanced telemetry, speech recognition, and intelligent systems of which he has received various patents. He is currently serving at NASA's Johnson Space Center as the Human-Computer Interface Technical Discipline Lead to develop advanced human interfaces, as well as serving as the displays and control subsystem manager for the Commercial Crew program. He is, I'm sorry, I got disconnected. He is a senior life IEE member, and you're most welcome, Mr. George, on this program. And the platform is over to you for exciting, enthusiastic learners of the Cambria International School. You're most welcome to the platform of Cambria International School. Over to you, Mr. George. Thank you so much.
Well, thank you very much. Can you hear me okay?
Yes, yes, you are very clear. Thanks a lot.
Okay. Okay. All right. Thank you. Thank you. Thank you, everybody, for those kind words, introduction. Thank you for inviting me. It's a pleasure to be speaking to all the students. I really enjoyed talking to students because you guys are the future. You know, you're the future that is going to replace a lot of us guys that have been in the space program for many years and, you know, will be retiring. So somebody has to take our place. And my mission is for many, many years is always trying to instill the interest in space exploration and also you know, just staying in school and being the best that you can. So I'm going to get my presentation going here, and hopefully you can see it pop up pretty soon. Let's see here. All right, can you see that first slide? All right, so hopefully you can see that. If not, please interject and let me know that you can. Sometimes technology can be wonderful, sometimes it can't. So I'm going to assume that everybody can see that slide. And so space exploration. All right, it's a big topic right now. Obviously, with SpaceX accomplishments, and I'll say a few words about Commercial Crew because I am involved with that later in my presentation. But here's what this is what you can expect. I'm going to be talking a lot. I have to say, maybe about 50% of the time about STEM, and you may well know STEM means science, technology, engineering, and mathematics, and that's very important in the space program. I'm going to be talking about astronomy, its impact in space exploration. Astronomy is very important for space exploration, as well as STEM and human spaceflight. Obviously, very critical, very important too as well. And just some concluding remarks. All right, so let's talk about the science and engineering. So what I want to first say is to make sure we understand what's the difference between science and engineering. Sometimes the line of those two is very blurry, but in essence, in science, you need not just the science, but you need the mathematics and you need the technology. Now, what does science seek to do? Science seeks to understand nature. Scientists try to understand nature. An example of that is like, for example, biology in a microscope, using a microscope to study, cell cells and blood and things of that sort. You're looking down at the microscopic level of science. And then, but there's also the bigger scope, the telescope. In astronomy, the scientists seek to understand the nature of star movements, of planet movements, and things of that sort. Now let's talk about engineering. Well, what is engineering? Well, engineering, like myself, I'm an engineer. We need everything. We need science, technology, engineering. You notice that I put the word art in there. And you say, art, isn't that drawing pictures? Well, yeah, it is. But also, I have found over the years that the artistic part of engineering and even science is to draw pictures of what could be, what can be. You have pictures that were drawn many, many years ago of what they thought life looked like on Mars, what life looks on other planets, and that's art. And art helps you to visualize, what can be. So I put art in there as part of STEM. So in fact, that becomes STEAM. And then the mathematics, very important. So engineer seeks to solve problems. We seek to solve the problem, like, for example, landing a man on the moon. There you see a picture of the Saturn ring that they were putting all the computers that guided the Saturn V rocket during launch. And of course, here's the launch of the Saturn. Very complicated, over 1 million parts that were involved in putting together the Saturn. So it took a lot of engineering, but it took some science too as well. So again, the science seeks to understand nature and engineering seeks to solve the problems. So let's talk about the science and engineering refresher. You've probably seen this in your classes. Interesting enough, there was a gentleman that's kind of like the father of scientific method. And if you were taught to school, basically it was to ask a question. That's the first important thing. Ask the question and then
Mr.
put a hypothesis.
Mr. George, I'm really sorry to intervene in between, but I would request you to please put your video on and your screen, if you could put it in the full screen mode, because most of the children are putting it on the mobile. So it would be nice if you could put it on a full screen mode.
Okay. Let's see. So let me know if.
Now it is perfectly fine. Thank you.
Okay. And can you see me?
Yes, we can see you. Thank you so much for that. Thanks.
Oh, you're welcome. You're welcome. Thanks for the feedback. All right. So here I'm showing a refresher of science and engineering, and there's similar processes in both methods, if you will. So the scientific method, there's a picture of a gentleman by the name of Hayata. I believe I pronounced correctly, but I'm not sure. So he's possibly the first world scientist that discovered the scientific method, a methodical way of defining a problem, designing an experiment, get the data from the experiment, and see if that data matches the hypothesis. Very similar in engineering. If you look at the right-hand side, it's define the problem, do the research, specify the requirements of the system, develop a prototype solution. In other words, you're building something, and then you get to test that something and gather the data and look and compare to see if it's identical, if it basically responds to the requirements. So in the sense of the scientific method and the engineering method, the hypothesis in engineering is requirements. The system shall have audio. The system shall have a propulsion system. That's called requirements. The system shall have a crew cabin for 4 astronauts. That's also a requirement. And so we got to build something to meet those requirements. And the only way to figure out if we did meet those requirements, very similar to the scientific method, is to gather data, test it, and see if it does meet the requirements. Now, let's go on to STEM in the space program. So let's look at the science aspect of it from STEM. Kinetic energy, potential energy is conserved, as we know. Potential energy, like for example, the rocket fuel. Until you ignite that rocket fuel, it's just potential energy. Once you ignite it, the kinetic energy of the ignition of that fuel is escaping gas. Well, the escaping gas is kinetic energy, and it creates the propulsion or the lift of the rocket. And then, of course, let's talk about technology in STEM. Technology is like the structured materials, the electronics of the computers, batteries. That's the technology. That's what engineers work with in developing spacecrafts. Now, if there's nothing there available that you can buy, we got to build our own, design our own. And that was a lot of that going on during the Apollo space program, because a lot of the things that was used in the Apollo program, and even before Gemini and the Mercury space program, it didn't exist because there was no market for space exploration. So NASA had to develop a lot of the technology to make space exploration with humans possible. Let's talk about engineering. Engineering is related to welding of the structure. How am I going to weld this kind of material? The material may be very brittle, very hard to weld, and maybe you have to use special type welding. And so that's part of the engineering process, is to figure out how we're going to put this structure together. Electronics and software to control the rocket. How are we going to design the electronics and the software to control this rocket? Testing to ensure that it works as expected. Testing is very, very important in engineering. Again, going back to the scientific method and the engineering design, testing is where you gather that data to prove your hypothesis in the scientific world, or in engineering to prove your requirements. And then mathematics. Oh my gosh, you cannot get away from mathematics. Equations to compute trajectory. There you have the kinetic energy, 1/2 times the velocity, mass times the velocity squared. And of course, velocity is a constant. So what changes the variable here is mass. Equations to design spaceships. Here you're seeing the equation of what they call the delta velocity of a spacecraft going from one orbit to another. So it has to do with mass, the changes in the mass taking over the natural logarithm. You have equations to predict the spaceship where it will be in time. That's how we predict. Like right now, the Perseverance, the Mars 2020, is on its way to Mars. Well, it has to do a lot of turns and the right turns, left turns, and all kinds of navigation in order to get to Mars. But that's all based on looking at certain stars and computing where it's relative to the Earth, to the star, and to the sun and Mars. And so equations are programmed into the computer systems that's taking right now Perseverance to Mars. And equations to predict the performance. When we're designing systems, we use a lot of equations and a lot of tools to help us predict how this system is going to behave in the real world. It's important because it's cheap early on to do designs using computers because you don't have to build anything. Building stuff gets very expensive. So if you use just a computer, it's rather inexpensive. And if it doesn't work out in your modeling, then you just change parameters and then you try again. And so you keep trying till you come up with a good design that you say, yeah, I think this design is going to work. Let's build it and let's test it to make sure that it's consistent with the modeling that we did. If it's not, there's something wrong, either the way that we designed it and built it or the model. If we find out the way we designed and built it was correct, it might be the model. So we have to update the models. So it's a constant updating of modeling and building systems in engineering and especially in space exploration. So past human spaceflight missions and programs. I'm just going to briefly go through this. A lot of this is history stuff. but I just want to kind of remind you of some of the human space programs that the United States was involved with. And so the first one was the Mercury program back in the 1960s. That's a long time ago. But we wanted to understand if humans could live and work in space. And so, we selected astronauts. All these astronauts were military pilots. Why were they military pilots? Well, because military pilots, and all these were test fighter pilots that basically tested high-performance jets, and they knew the risk in flying high-performance jets at going at Mach 2 or Mach 3, the speed of sound. And so they understood the risk, and they understood the risk of being launched into space by a big rocket with what they called a controlled explosion is the term that they use in launching the rocket. So very dangerous, and that's why they chose military test pilots. So what was some of the outcomes of it was to learn to eat in space. Can food stay down in your stomach? And also, can we do spacewalks? Okay, this is Ed White doing a spacewalk out of a capsule. And so we had to understand, what does it take to do spacewalks? Now, in the Gemini program, it was the bridge to the moon. The Gemini program now had 2 astronauts, and you needed 2 astronauts because the Gemini space capsules were much more complicated. In fact, Gemini had the first onboard computers ever in human spaceflight. Gemini program did not have computers on its capsule. A lot of the computations were done on the ground and then sent up to the Mercury space capsule by RF communications. And so we learned to dock in order to understand how can we take 2 spacecrafts coming in separately here and then docking together. This is very critical for the Apollo space program. So in the Mercury program, the key science research and engineering challenges was the science of human body response to microgravity and the body response to launch and life supports. What does it take to support the life of humans in a place where it's not meant for humans to live in? And then the key science in Gemini was the science of, again, learning to live more in a microgravity environment for a longer duration. Gemini was up there for about 2 weeks, as opposed to Mercury, which was just a couple of days. And so we learned to do a little bit more about living and working in space for a longer period of time, and rendezvous and docking. Now, let's talk about Apollo. That was the one that got us to the moon. There was a lot to learn about the Apollo space program, because this was now the first opportunity to learn to live and work on another planet for the first time ever. And of course, Apollo 11 was instrumental in landing the first humans on the moon. Neil Armstrong and Buzz Aldrin were the first 2 astronauts on the surface of the moon. Afterwards, there were 10 astronauts that would follow Buzz Aldrin and Neil Armstrong on the surface of the moon to live and explore there. And of course, there's the space shuttle, the reusable spacecraft. That's the program I started with when I first came to work at NASA. And the space shuttle, even though it's 1970s technology, very, very complicated system. It launched like a rocket, orbited like a satellite, but returned to Earth like a jet airplane. So it had a lot of capabilities, and of course, they sometimes called it a truck because you could launch big things. Like here, you're looking at the Hubble Space Telescope being launched from the space shuttle, and then also it was used to retrieve the Hubble Space Telescope when it had mirror problems, and put it on the space shuttle so they could repair it and put the new corrective lenses and computers, and then send it off into space again. So in the Apollo space program, there was a lot of key science and engineering challenges. Guidance computers, we have to develop guidance computers to take us to the moon. Life support systems to support humans reliably on the moon and return them back safely to Earth. Rendezvous and docking, human operations on the moon surface, extra vehicle activities and communications as well. It takes about 1.2 seconds to reach the moon for communications. Not too far away, but still we had to understand, is that fast enough to communicate with people on the moon? As you, I don't know if you've heard or saw the Apollo 11. Apollo 11 was in trouble early on because the automation system was going to land the Eagle on a rocky area, which could have destroyed the Eagle landing craft. And luckily, Neil Armstrong saw the situation and turned off the automation control and took over manually and safely landed the Eagle on the moon. On the space shuttle program, oh my gosh, there was so much to learn there about food, about life support, complex assembly. And then being there up for a longer period of time, we started to learn about biology experiments, to learn more about living and working in space, and developing drugs that can only be developed in space because of the microgravity environment. And then now that takes you to space station, which is currently orbiting the Earth at about 260 miles above the Earth's surface. And the microgravity environment, you hear sometimes the term zero gravity. There's no such thing as zero gravity. It's microgravity. There is a small amount of pull, if you will. And of course, the astronauts, you see them floating in space. Well, they're not really floating in space. They're falling. Everything on the space station and everything in the space station, including the crew, are falling around an orbit. And that's why it looks like they're floating. They're really falling around the orbit. And the orbit, as long as they keep going 17,500 miles per hour, they keep orbiting the Earth. But there's some interesting things about the microgravity environment if you think about the science that can be done on the space station. There's an absence of buoyancy and sedimentation. So on Earth, because of the microgravity environment, it pulls everything down. But in the microgravity environment, things tend to float around. And so you can investigate some of the hidden properties of the material in the microgravity environment that you cannot see in the 1G environment that we're accustomed to here on Earth. And the other thing is the absence of convection. Okay, so like for example, heat. If you've ever seen, let's say your mom cooking on the stove, and the water starts to boil, and you see the vapors going up. Okay, so there's a convection going up. But in the microgravity environment, there is no convection. The heat would just stay right around the area where it continue building up, and so you tend to learn about how to take heat away in the microgravity environment as opposed to the 1G environment that we're accustomed to. So you can study properties of different materials and how heat behaves in that material in a microgravity type environment. Also, the absence of hydrostatic pressure. Well, here on Earth, if you go down further and further, like for example, into the sea, I do scuba diving, and as you go further down into the ocean, the pressures get more and more bigger. That's not the case in the microgravity environment. So you take advantage of that by doing some experiments that you don't have to worry about that hydrostatic pressure. And of course, this is called containerless flow. So here you see water on Earth that basically fills a bowl, okay? So here's a bowl, and the water's in there. But in microgravity, there is no containment. The ball of water becomes a ball. Here is astronaut Scott Kelly that spent over a year in space with what looks like a little toy ball, but it's not a toy ball. That's actually water, and he painted what looks like the Earth, but that's really just water. But there's also things at space station that we learn, conduct experiments. Okay, so this is a refueling experiment in one of the Japanese modules, and this was to learn how to store gas at very, very, very cold temperatures. We call it cryogenic storage. And so you can store like liquid methane that's very, very cold. in this containment. So why are we doing that? Well, when we go deep into space, we're going to have ways of storing fuel and also storing these gases that are used for life support systems for generating oxygen for the humans. And so we have to make sure that these things don't leak in space. And so, because we don't want them to run out of fuel or run out of oxygen too early in a space mission. There's also, believe it or not, this is a toilet on space station, and this guy's repairing that toilet. Having a toilet, a good working toilet in space is not very important to astronauts as well. So we need to understand better how to build better, reliable toilets. In fact, our station, I think, got a new toilet that's going to be more reliable than what they have right now. And of course, conducting human behavior and health experiments in space. Here again is Scott Kelly that spent over a year in space. And when he came back, he was not in very good shape. Our bodies were not meant to live in microgravity for a long period of time. We're so accustomed to living in a one gravity environment, 1G environment, that you go in a weightless environment or microgravity environment, and things like blood pressure, sinus. There's no sinus drain in space. If you have a sinus and you have congestion in your nose, it's not going to go flow out. It's not going to flow out of your nose. It's going to stay in the back of your eyes, and it builds up pressure in your eyes, and that's affecting the vision of astronauts as well. And of course, the blood circulation, because the blood is not understanding why there's no one gravity environment, to keep the blood from the feet to go back up to the head. And so, they get dizzy and things of that sort when they get back to Earth. So let's start talking about astronomy and its impact in space exploration, because astronomy is the other part of space exploration. Sometimes people think, well, space exploration is about sending rockets and robots to other places and humans and stuff of that sort. But it's not just that. It's also looking out at the stars and seeing, what's out there and why is things behaving as they are. If you look at the contributions of space exploration, it began with just the naked eye. Scholars, developed an understanding of the stars and planets and their movements based on observation and writing down those observations. Okay, this is important for whether you're in science or engineering, is write down your observations. I tell my engineering interns, I usually get interns that are from universities, and I tell them keep a notebook of everything that you do, because that becomes very important later on, because you start going back and seeing what you did, how you did it, what went wrong, what went right. So observation, not just the observation, but also writing down of those observations is very important. The development of the telescope in the early 17th century, they started to look at more details and more accuracy, how the planets behave, the rotation of the planets, the location of planets. Of course, Galileo Galilei, understood that it wasn't the Earth that was the center of the solar system, but rather it was the sun that was in the center of the solar system, and planets rotating around the sun. And then, of course, we had more technological advances now in the second half of the 20th century. The Hubble Space Telescope, that's, oh my gosh, it's gathered so much data over the years. It's incredible. Here's a picture of Kepler. Kepler kind of was somewhat what I consider the unsung hero of space exploration, but Kepler was a telescope that recently just retired because of how old it was getting, but it captured something like 3,000 exoplanets that it discovered. Incredible discoveries of exoplanets. And of course, an exoplanet is pretty much a planet that it's a possibility there could be life on that planet because of its location to the sun. Okay, so planets have to have a certain location relative to the sun in order to provide a opportunity for life to live. Okay, we're lucky in Earth. You know, we're the third planet from the sun, but we're just at the right location for not too hot, not too cold. Mars is part of what was at one time part of that. And we're not sure what happened to Mars that died. And that's what we're going over there with Perseverance to learn more about Mars. And of course, here's the Higgs boson, theoretical part of space exploration is trying to understand this particle. They call it the God particle. That's supposedly that gave mass to matter during the Big Bang theory. So that's part of space exploration and learning and understanding how our space has developed. Again, this is science also, because remember I said earlier, science seeks to understand nature. And there's a lot of nature out in space, and we still need to understand a lot more about it. And of course, hopefully in the next couple of years, they're going to launch the Kepler, I'm sorry, the James Webb Telescope. And the James Webb Telescope is going to look further into space. You know, people say, wouldn't it be great if we had a time machine to go back in time? Well, if you look out at night, you all are basically looking back at time. You're looking at, obviously, light from stars far away that's finally reaching your eye. But it took millions and billions of years to get to your eye. So you're actually looking at history when you go out and look at the stars. Now, James Webb Telescope is going to be looking further, deeper into space than Hubble did. And hopefully we can go further back than 14 billion years, which Hubble did. And maybe we'll see even earlier signs of indications of the Big Bang theory. All right, so science in support of exploration, you know, understanding a solar system, as I mentioned, you know, these are nebulas, okay? So, nebula sometimes will have stars, you know, this is the cradle of star formations, and understanding how that happens. Understanding exoplanets, as I mentioned, Kepler was one that captured a lot of potential exoplanets similar to our Earth. And here's a rendition of one that looks very close to its sun, but could potentially have life on that planet. And then here's Mars Science Laboratory, very similar to the Mars 2020 Perseverance. Now, one of the big differences between the Mars Science Laboratory that's currently right now there and the Mars 2020 Perseverance is that Mars 2020 is going to have a lot more experiments in there to learn about Mars. One of the things that Mars Perseverance is going to have is what they call in situ resource utilization. And it's basically going to be the first time ever that it's going to collect soil from Mars and extract oxygen and to see how pure that oxygen is when it extracts it. Why is that important? Because one day we're going to be going to Mars with humans, and we need to learn how to live off the land. And so we need to learn whether we can develop the technology to produce oxygen and also produce water and also produce fuel from that soil. Perseverance, interesting name, Perseverance. I use that term a lot because I have to say that I struggled in school, especially at the university with engineering. And the term perseverance comes to mind because it's basically you continue doing, you're reaching your goal despite setbacks and despite obstacles along your way. As I learned, the only obstacles in your way are the ones that you produce to yourself. Anything is possible. And that's one of the reasons why really...
Mr. George Salazar.
Yes.
Can you hear me?
Yes.
Actually, I'm receiving a lot of requests from the students and the parents to post questions to you. So will you have time to address the questions?
Yeah, sure. Okay, I'll have to get out of this presentation mode. Stand by.
Yeah. Please, so that we can begin the question and answer session with the children.
Sure.
Yeah.
All right.
All right. Thank you so very much, Mr. George Salazar. That's wonderful of you. I think, Loveleen, madam, you can take the names of the students and give them opportunity to ask question to the NASA scientist, Mr. George Salazar. Thank you.
Sure, ma'am. Thank you. I request Arna Panda from grade 3B to put forward her question. Arna Panda from grade 3B.
Loveleen, madam, if she has a problem with the question reading, you may read out her question and she will listen to the answer. Thank you.
Okay, I guess I didn't pick up on where's the question coming from. Is that question number one or?
The question number 2.
Can
Number
you please
2?
read out the question? Loveleen, can you please read out the question?
Yes, ma'am, sure. The question is, when can we expect colonization of Mars, and when will human race actually settle there?
Okay, that's a good question. So colonization of Mars, it's very difficult at this point in time to figure out exactly when. So we're going back to the moon. Why are we going back to the moon? Because we need to go back to the moon to learn to live and work on another planet. So it's the moon that's going to help us develop the technology that's going to take us to Mars. You know, like I'm going to give you an example of why it's important to go first to the moon than Mars. Let's say, for example, you've never gone camping in your life. And so let's say down the street is a little park. And you say, I'm going to spend the night at that park. And of course, you know, temperature's fine and everything. And so you take your little bit of food and things of that sort. And you go there and you come back the next day and say, oh, that was fun. And then you say, okay, let's go to Mount Everest and go camping there. Big difference between camping just outside your back door and going to Mount Everest. Same thing with Mars. Mars is a big step. And so to answer your question, if we could do good engineering, good science, and get everything ready in the next 15 years, I think we'll be ready to go to Mars and first live on Mars and understand what's it going to take just to have people living and working there before we can colonize. You don't want to send a whole bunch of people to a place that is not ready to receive people. You don't want to send 1,000 people to a little island that has no food, no water, and no way of living there. You know, you got to have everything ready. Just like if you're going to move into a house, you know, that house has food. I'd rather you have a house that has maybe food, water, everything that you need, the restrooms and everything. And now you can move in. Same thing with colonization. So to answer your question, we're looking at about 15 years. Maybe even longer, 20 years. It's very challenging. I'm hoping many of these students here are going to find ways to accelerate that, but lots of difficult problems to solve for humans to live on another world.
The next question may be asked by Vaishnavi Verma from grade 5.
Can you repeat the question, please?
Sure. The question is Pluto still a planet? If no, why?
Well, you know, Pluto is one of those planets that one day it is and one day it isn't. So Pluto, in theory, is considered a planet In fact, I think New Horizons had determined that there was some kind of a weak magnetic field there, kind of like Earth's magnetic field. And but the problem about Pluto is it's got a very unusual orbit around the sun, and sometimes it goes way out and then comes back in. Yeah, I think that question is going to be asked for a long period of time. But at least New Horizons went over there and discovered a lot of aspects of Pluto. I mean, from all standpoints, it is a small planet, no different than perhaps Mercury. But it's just the way scientists sometimes will decide whether it's a planet or not. And to me, the ones that I've talked to, they think it is a planet, but it depends who you talk to. But I consider it a planet.
Now I request Manasvi Pote from grade 11 to ask her question.
Am I audible?
Yes, you are.
Yes. So good evening, Salazar sir, and all the dignities. So my question is that what is the reason behind the normal Earth time and the interstellar time in the space?
Say that again, please.
What is the reason behind the normal Earth time and the interstellar time in the space? The difference between them. Why is that the difference?
Oh, all right. Now you get into some really science stuff. One of the things about time is like Einstein said, it's kind of relativistic based on where you're located. Interstellar time, it's if you think about time, it's got a positive direction, and so time on Earth, it's something that we're accustomed to, and this is one of those difficult problems to discuss. But you have time on Earth, and the clock's ticking. Seconds. Seconds. 60 seconds in a minute. But on another planet, it could be different because of its orbit relative to where we're located. So, to discuss time, you have to say, well, the time, like for example, on Earth and Mars, the time is different, because of the rotation of the Mars rotation around its axis relative to the Earth, and so the time around Mars is shorter than Earth, but still time marches forward. So it's a matter of where you're talking about time, because the universe is so huge. Interstellar time is so huge, and that's why they talk light years, right? They say Alpha Centauri is 5 light years away. Well, what's 1 light year? Well, 1 light year is traveling at 186,000 miles per second, for 5 years. And that's the distance, but the distance is so long. So if 1 second here, it takes a long time before we say, well, when is it a second over there? We still don't know that relationship. All we know is that it takes a long time to get to that point. But it's one of the things that we need to actually send to different parts of the universe, little timepieces, if you will, and let them send beaming back information to us, and so we can now get a time difference between all the different points in the universe, or this as far as we can go. But space is so big, I don't know if we're going to be able to accomplish that. Maybe you'll come up with a better way of doing it. Thank you.
Thank you, sir.
You're welcome.
Now I request Abbar Swara from grade 12 to ask his question.
First of all, a very good evening to all the dignitaries. Thank you, sir. Your session has been really great, and we've had a lot to learn until now. So, coming to my question, it's basically about the structures on the architectural designs of the rocket. Why do the SpaceX boosters that are used in the Morgan Day rockets and was used in the Mars 2020 have a narrower shape or a design as compared to the old NASA boosters? Like, have there been some practical developments with time when the engine, or have we just discovered an easier way for the booster cutoff systems?
Well, you know, the SpaceX rocket is no different than if you saw pictures of Mercury, Gemini, even Saturn. These are what they call um, rocket um, rocket stacks, if you will, as opposed to space shuttle. Space shuttle had two socket rocket motors, and then the main engines underneath it. And that was the reason for that was because of how heavy it was. SpaceX Dragon is not as heavy as shuttle, and obviously it wasn't as big as space shuttle. So it's not so much that SpaceX has come up with anything revolutionary. It's just a matter of how big do you want the rocket to launch something as big as Dragon? And that's the whole nature of engineering rocket propulsion, is that you're trying to build a rocket at the lowest cost possible, at the minimum weight possible to launch your system. So for SpaceX, the rocket stack that looks like a tube is perfect, for the SpaceX. But you see SpaceX for the big vehicle, you see that it's got a whole bunch of different stacks going out sideways because it takes a lot of energy to lift something that heavy into space. So you start seeing spacecrafts, especially if they start going to deep space, like for example, Perseverance. That's the Atlas rocket had, I think it had five little solid rocket motors around it, and they separated when it got up into space. So it's just a matter of what you're trying to launch into space.
Sir, just a quick follow-up. Has the basic engineering and used within the boosters remained the same throughout the generations, or have there been any efficient upcomings in the same?
I'm sorry, could you repeat that, please?
Google boosters that were used by NASA in earlier missions, and the SpaceX boosters use the same technology, like the engineering technology, which provides the boost or the force required for the rocket.
Yeah, I mean, the booster rocket technology is pretty much there's two kinds. There's the liquid, and then there's the solid. And of course, there's a difference between the two. Solid fuel rocket technology. You see, we're still tied to all this chemical rocketry, and we need to get away from that if we want to go deeper into space. But solid rocket motors, basically, once you turn them on, they will not turn it off, not easily, as opposed to liquid engines. That's why space shuttle and even SpaceX, they use liquid rockets because they can turn them off at the last second. If something's T minus 10 seconds and counting, there's a lot of checks going on very fast. And if something goes wrong, they shut off the engines before they take off. So the technology hasn't changed, but it's still very reliable.
Thank you, sir.
You're welcome.
Now I request Adi Srivastava from grade 3 to put forward his question.
Good morning, George, sir. Namaste.
Hi, good morning.
I am up. Good morning, sir. My question is that how come and who has discovered the space initially?
Okay, who discovered space?
How come and who has discovered the space initially?
Okay, if you're talking about space, outer space, or space in general, how can we discover that, and who discovered it? So the discovery of space it goes back to even cavemen. When they first looked up to the sky, at the sky, and saw all these little bright stars in the sky, and it's just space has always been around us, but Who discovered it? I mean, it was long time ago when when we humans first started looking up at the stars, and of course that's really interesting because when we start looking out, you start seeing, asking questions. That's important, asking questions. And thank you for your question. Is who discovered this? Why are we looking out into space? And that's the whole reason of why humans are very curious people, because we want to know what's out there and how did that come to be. But for space, it's hard to say who discovered space, but I would have to say it was the first humans that looked up at the sky and saw stars for the first time. Good question, though.
You're welcome, sir. Thank you.
Now I
You're welcome.
request Sanvi Patange from grade 4 to put forward her question.
Good morning, sir. My question is, what will happen to the sun after a billion years?
Well, that's a good question because the sun has so much energy, and eventually it's going to run out of fuel. The thing is that 1 billion years, I think it's going to be around. Right now, the thinking from a scientific standpoint is that it has enough fuel for 4 billion years. Now, after 4 billion years, what's going to happen to the sun? Well, basically, the theory is it's going to, because of the size of the sun, it's going to expand out into our solar system and possibly taking Earth with us. But 4 billion years from now, I'm hoping that civilization has moved somewhere else, and then it's going to shrink back down and then become a very small ball and just die. But that's 4 billion years from now, and again, I hope civilization by that time has discovered the technology to perhaps have us go to other places, other solar systems, and learn to live in other places. And so by that time, we won't care what happens to the sun because we're going to live somewhere else. Good question, though.
Now I request Sayam Dharam Dasani from grade 12 to put forward his question.
Good evening. First of all, good evening, sir. Thank you for being here with us. And my question to you is, why does NASA present digitally constructed composite renderings of the Earth's shape based on the satellite travel over the Earth, and as also acclaimed by NASA's digital Photoshop technician, Robert Simon, uses CGI and restricts from publishing them to publicly accessible sources, instead of availing the actual shape of the planet without manipulating it to fit the proclaimed ovular description?
All right, so I guess what you're saying is that the Earth is kind of viewed as a perfect circle when it's not. Yeah, well, so it's not a perfect circle. It's got, because it's been pulled from different directions. There's a lot of gravitational effects happening on the Earth that causes it to elongate a little bit. But the elongation is almost from a let's call it from a public standpoint. The public probably may not really care that the Earth has one side of it maybe 4 feet elongated further than the other side. In all practicality, if you look at pictures from the Apollo space program, if you look at Earth, what does it look like? It looks like a round ball. But if you're to look at it very closely, you will see the elongations of it. Now, I'm not familiar with Robert Simon's work, but for the most part, if you were to show the Earth a little bit elongated, it probably would not mean that much to the public, and maybe that's the issue. But I can tell you that it's certainly not flat.
Yes.
Now I
Thank
request
you.
Thank
now
you
I
so much,
request
sir.
Akshata More from grade 11 to put forward her question.
Am I visible, ma'am? Hello.
Yes, yes,
Hi.
Hello, sir. Greetings. I am Akshata from grade 11. I had a question. I just read in newspaper around somewhere that there's recent discovery of a planet which is 3 times to 4 times bigger than Jupiter. So I wanted to ask, will it really affect us, like gravity types? And how can you elaborate what the discovery actually means?
Okay, could you repeat the question, please?
Sure. I read somewhere that there was discovery of a planet which is 3 times bigger than Jupiter. Like its rings were also 4 times bigger than Jupiter.
Oh, well, yeah, I'm sure there's planets much bigger than Jupiter. The thing is that there are suns out there that are make our sun look like Mercury compared to the sun. There are just some huge, and that's the beauty of discovery and exploration is that we keep discovering something new, and what we think we know everything, something new comes along. So I wouldn't be surprised that there's a discovery of planets 4 times the size of Jupiter. But you have to keep in mind, also think about the physics and science of a larger planet and what would life look like on a larger planet? Well, if you have a larger planet, sometimes the gravitational pull is bigger. And so what does that mean? You have a bigger gravitational pull on the ground. So that means that humans or whatever they are, what do they look like to live on something like that? What do they, if the temperatures are very hot, very cold, what do they look like? We still don't know what life looks like on other worlds that were discovered. Like I mentioned, Kepler discovered almost 3,000 exoplanets. And so the question, this is astrobiology, astrophysics, is to try to answer the question, what do humans, what does life look like on other planets that we are not, that we don't know?
Thank you, sir.
You're welcome.
Now I request Himani Yadav from grade 12 to put forward her question.
Good evening, all the dignitaries, and good morning, sir.
Okay, I can barely hear you. I can barely hear the person.
So, am I audible now? Hello.
Yes, Himani.
So, am I audible?
Imani, speak a little louder.
Yes.
Okay. Just speak a little bit louder, please.
Yes, sir, sure. So my question to you is that right now, as we are going through a pandemic and we don't know what the future holds for us. So if ever in the future humans need to leave Earth and go on another planet, so do you think would it be possible for every human, like all of them, to do an interplanetary mission? Not only just economical or physical wise, but rather we also know that astronauts need to meet up certain physical requirements health wise, so and not every person is fit for that. So would it be possible for all of them to do so?
Well, okay, so right now the population of Earth is somewhere around 7 billion people. And so right now we can only launch rockets with 4 or 5 people. So we're talking about massive massive exodus from Earth, and I think one day it'll be possible because we keep learning and evolving, and that's the beauty of science and engineering, is that we keep growing and learning more and more, and that's important because otherwise, if we didn't, we'd still be in covered wagons being pulled by horses. So I think it's possible. It's just a matter of how can we do that um, in a way that's not too expensive. I mean, just trying, every time I see Starship, the Star Trek Enterprise on television, Friends of mine at work, we kind of argue about what's that going to cost. We're looking at building a Starship Enterprise that I think they have 400 people on board. So 400 people on board that Starship Enterprise. We're talking about maybe in the vicinity of $120 trillion to build something like that. So we need to find cheaper ways, and that's why we have commercial partners like SpaceX that perhaps can develop better techniques, better ways of finding cheaper ways of going to other planets. Good question, though.
Thank you so much, sir. Thank you.
Now I request Samiksha Malekar from grade 6 to put forward her question.
Yes. Good evening, sir. My question is, NASA investigates how dormant viruses behave during spaceflight. Can it be applied by COVID-19?
Let's see. Can you repeat that, please, one more time?
Sure, sir. NASA investigates how dormant viruses behave during spaceflight. Can it be applied by COVID-19?
I think so, because obviously, COVID is a virus, and the thing about it is, as I mentioned earlier, the thing about microgravity environment is learning things in microgravity that you cannot see on Earth here, the 1G environment. So they're looking at viruses in space, but it's very dangerous because what happens if those viruses get out on space station? It's a very closed environment. They can't just go outside if the virus gets loose. And so it's they have to be very cautious how they design and build. This is where engineering and science come together, is how do we build a container to put a virus as deadly as COVID in there and keep it from getting loose in the space station and affecting all the astronauts and killing them. We don't want that. And so, but it is possible. It's just a way of finding ways that are safe and very effective of doing that. But that's a good question.
Now I request Shlok Pahadi from grade 7 to ask his question.
Hello, sir. My question is it true that the universe also has a fundamental clock-like property which is ticking and has different parameters?
All right. You broke up a little bit. Can you repeat the question again, please?
Yes, sir. Is it true that the universe also has a fundamental clock-like property which is ticking and has different parameters?
Oh, wow. You're breaking up. Okay. Let's see. If you can move the mic a little bit further away.
If it is not clear, Loveleen madam, please read out the question.
Sure, ma'am. The question is it true that the universe also has a fundamental clock-like property which is ticking and has different parameters?
Good question. The universe, it's interesting. So I know there was an earlier question about time, and right now, there's a lot of investigative work about time, and of course, one of the things that time has is that pretty much all the scientists agree is that it goes in a forward direction, and it does not go backwards, at least as far as we know, other than the time that's already passed. And of course, you see that in the stars when you're looking out at night. But does it have a fundamental clock property? I would say that we as humans perceive time the same here as that we would perceive it on another planet. It's just a matter of the time there, but it's still 60 seconds here is 60 seconds on Mars, 60 seconds on the moon, 60 seconds on Jupiter. But each one of those has their rotation. Obviously, their days are longer or shorter. So, that's a good question to that's a good question to that you ask, and you might be the person that comes up with a way of defining that fundamental clock property. But I mean, at this point in time, it's pretty much the same everywhere. I know that they did an experiment on space shuttle to talk about to investigate relativistic time. In other words, as you're going faster and faster, time gets slower and slower. And sure enough, for the astronauts on the space shuttle, they saw their clock going a little bit slower relative to the Earth time based on the speed. So, but it would seem like the clock on shuttle. I talked to astronauts. They had watches, and so they used their watch, and so the time was the same there as it was at where they left Earth. So it's a matter of how do you define the fundamental clock fundamental clock property relative to where you're located, and that's the question that perhaps you can answer one day. Good question. Thank you.
Now I request Sania Wastrad from grade 12 to put forward her question.
Good evening, sir, and good evening, everyone.
Hi.
My name is Sania Wastrad. First of all, sir, thanks a lot for this session. And coming to my question to you is there really something present in the space called as dark matter?
So dark matter is one of those we haven't seen yet, but apparently it's one of those phenomena that are perceived or seen in an indirect fashion. And so apparently the space is made up of a lot of dark matter, and they think that's what's causing the expansion of the universe, pushing outward. But we haven't seen dark matter physically, and maybe it's kind of like the Higgs boson particle. We haven't seen it, but obviously the data suggests that it does exist by indirect measurement. So you can look at stuff indirectly or directly. You can see that the sun is very bright, or that indirectly, you're looking somewhere away and you see some kind of reflection of the sun. And even though you're not looking directly at the sun, you see that spot getting brighter and dimmer. So indirectly, you're seeing the behavior of the sun. And that's the same thing with dark matter. Even though we can't see it directly, we can see it indirectly. So the data suggests it's out there. We just have to find a way how to see it. So maybe you'll come up with a way to expose it that everybody can see what it looks like.
Yes, thank you.
You're welcome.
Now I request Diya Srivastava from grade 6 to put forward her question.
Good evening, sir. And first of all, I'm Diya Srivastava from the Cambria International School. And first, I'd like to congratulate the NASA and you for completing 50 years as a space agency. Congratulations for that. And putting forward my question is to you, why did NASA spend huge money developing a pen that would work in space when a pencil can do that?
Okay, that question's been around for a long period of time. Good question, though. So, you've heard that on the internet, sometimes information can be truthful or it can be false. And so the real story behind the space pen is that NASA did not spend money on it. The name Fisher, he decided to build, using his own money, a pen that could be used in microgravity. And so he built it, and he told NASA, "Hey, would you like to use this pen?" And so he did. In fact, I have a Fisher Price pen here. I guess I'll have to look for it. But anyway, it's a pressurized capsule. But anyway, the story is that NASA did not spend a penny on it. It was Fisher that put his money into building that pen and say, "Hey, NASA, would you like to use this pen? It's very beneficial." Pencils. Okay, the Russians used pencils. Well, why did the Russians use pencils? First of all, because they couldn't afford building a pencil. They found that a pencil was beneficial. But there's some drawbacks with pencil that I think everybody needs to understand. That because pencil has that the pencil lead, the pencil part that you write on. If that breaks off, it's very conductive. What does conductive mean? It means that it can conduct electricity. So what happens if that pen piece breaks off and gets into an electronic circuit? It could short circuit a component and cause a problem. So pencils, even though they're cheap, are there's a hazard with them. And so, yeah, the space pen, NASA didn't spend a penny on it. It was all done by a company that said, hey, I'm going to develop something for NASA, and let's see if they want to use it. When he showed it to NASA, they said, yeah, we'll use it. Good question, though.
Thank you, sir, for answering.
Now I request
You're welcome.
Sethi from grade 9 to put forward his question.
Good morning, sir.
Hi.
I'm Gurinder Sethi from the grade 9. So my question to you is, does the multiverse exist?
Does the multi-universe exist?
Yes.
It's one of those, and maybe you heard my answer to another question. Right now the theory is that we have what they call parallel universes. Okay, same thing as multi-universe, and so the theory is that in each universe something different happens. Here's the problem. We have not physically seen it. We just have a theory. And so going back to the scientific method is you form a hypothesis, right? The hypothesis, the multi-universes exist. And so that's your hypothesis. And so the difficulty scientists are having right now is formulating an experiment to show that. And so, the theory is there, the hypothesis is there, but we just need to find a way to either directly or indirectly measure or sense or take a picture, however you want to call it, of that multi-universe. So there's one theory that it talks about how people have seen, strange beings appearing right before their very eyes, and then they disappear. And so, one theory is that we're colliding with universes, that things are happening and these things somehow show up. But there's no proof. I mean, I don't know if you know who Carl Sagan is, but Carl Sagan was a very famous astronomer, very famous scientist in the United States. And he said that extraordinary events require extraordinary data. Okay, so if something is extraordinary, out of something that we're not accustomed to, we need to have the data to prove that. And so at this point in time, it's theory, but maybe you will be the one to discover that. So that's kind of exciting to know that there's still things to be discovered out there by very smart people like you all. Good question, though.
Thank you, sir.
Now I request Sanskar Sharma from grade 7 to ask his question.
Good, sir. My name is Sanskar from grade 7A. My question was that how do the astronauts that after the ISS mission, how do they came to Earth and how do they behave?
I say, repeat that again.
If we see that there are astronauts who live for months in ISS, so how can they get to Earth after some months?
Okay, so
Navleen, madam, please.
Right now
the question is how the astronauts come to Earth after going to the space, and how do they behave, and where do you keep them?
Okay, three-part question. All right, so how do they come to Earth after being on space station? So space station has, right now they have two At one time, they had three basically return vehicles, but they have two Soyuz space capsules in there. So when it's time to come home, they get in one of those Soyuz space capsules, soon to be replaced by SpaceX one day. But right now they have Soyuz, and so they get inside the Soyuz and they come back and they land in Russia. They land on hard surface, which there's good and bad. The bad part is that you can come crashing down on hard surface. But anyway, they come back to Earth by using the Soyuz space capsule right now. Hopefully, SpaceX will be putting those crew return vehicles there, and they come back to the United States. How do they behave? Well, they have to relearn how to live in a one gravity environment again. They've been up in a microgravity environment for 6 months, and so their bodies are weak, their bones are weak because they didn't produce as much calcium as they do here on Earth. And their eyesight has some problems. They have problems with their circulation of their blood, and so they have to be kept. That's the last part of your question. Where do you keep them? They're kept in a medical facility for a period of time to monitor them and observe their medical condition to make sure that they're okay before they release them to going home. That's a good question.
Thank you, sir.
Now I request Dhananjay Tiwari from grade 11 to ask his question.
Good morning, sir, as it is morning there.
Hi.
So my
Dhananjay,
question...
a little louder.
Okay. So, sir, my question is that does every black hole contain a singularity?
Say that again, please.
Louder. You got to be still louder, Dhananjay.
Okay, ma'am. So, sir, my question is that does every black hole contain a singularity?
So here's the thing. So far, the black holes that have been discovered, to my knowledge, have a singularity, and so I would assume that all others have a singularity. But in science, you can't assume. You have to get the data, to prove your statement. That's the beauty of science and engineering, is that you don't say something unless you have data to support it. And if you don't have data to support it, you shouldn't be saying that. But for the black hole to have a singularity at this point in time, what we know at this point in time is that every black hole has a singularity. So any future discovered black holes, there's a likelihood that it's going to have a singularity. But we don't know that totally until we start exploring more black holes, which is somewhat of a challenge. Good question, though. Thank you.
Next question is by Hariti Soya from grade 10. The question is, can artificial oxygen and gravity be created on Mars for the existence of lives?
Yes, it can. Okay, so that's the theory. So again, you got to prove your theory, as any good science or engineering student would do, or engineering person would do. And so that's, as I mentioned, Perseverance. Right now, it's on its way to Mars, and it's going to have a experiment called MOXIE. And MOXIE is what they call in situ resource utilization experiment to see if they can take dirt, let's call it dirt from Mars, and convert it into oxygen and also possibly water. So you can create oxygen. Gravity is not that simple, all right? You cannot create artificial gravity on another planet easily. It's just the nature of the composition of the planet, mass. It is relative to other solar system bodies in our solar system. So that's been a discussion of creating artificial gravity on our way to Mars, so that way it can help astronauts not have a lot of medical issues that they experience being in microgravity for a long period of time. So they talk about rotating a spacecraft at a certain speed to create an artificial gravity, but it's very, very difficult to do that. But you cannot do that on Mars. It is what it is as far as the gravity. At least at this point in time, with our limited science and engineering capabilities, oxygen, that is very, very possible, and that's certainly something that we are very interested in, and that's why Mars Perseverance has that science experiment, MOXIE, to see if it can take dirt and create good oxygen that astronauts can breathe. Thank you.
Thank you, sir.
Next question is by Radesh Jagdale from grade 10. Radesh, you need to unmute.
Good morning, sir. My question is, how do we know that universe is expanding?
All right. So, I mean, that's actually something that was discovered, several years ago by some scientists. I think at Bell Labs or something. They saw the snapshots of the universe through astronomical observations of a red shift. And so, if you know the terminology Doppler shift, so things coming close to you has a certain frequency that's related in terms of light, and then it's a kind of and then things leaving are associated with another light. So they look at the difference of those frequencies, and they saw that the expansion is going in a frequency suggesting that it's moving away. So if you ever, I don't know if you ever experience an ambulance coming toward you, you hear the and then when it's going away, it goes so it goes higher and then lower. So when it's moving away, the frequency has shifted to a lower frequency, and so you can actually represent that by light, and that's what's happening in the universe. They're seeing that shift of lower frequencies, everything moving out in different directions, and that's basically the universe expansion. Going back to dark matter seems to suggest that it's causing that expansion, but we still haven't seen that objectively. We have to find a way to see that dark matter actually pushing everything out in different directions. Good question, though.
So just to confirm that I understood the answer, you mean that the things that are there in the space, they are going far, shifting. The difference between the stuff in the space is increasing, right?
The frequency is changing. Yes, it's the astronomical observations and the data coming back from the different planets. See, they can look at one solar system, or they even go better than that. They look at a galaxy, because there's billions of galaxies out there, and they can compare one galaxy against our galaxy against another galaxy and say, how's this one moving relative to ours, and how's that one moving relative to that one? And so you can see how things are moving, and if everything is moving away from each other, what does that suggest? It suggests is an expansion going on. So you can make the observation in a direct fashion.
So just a follow-up question. Let's say if we are standing, two people are standing in the room, which has a...
Please limit your questions to one question, please. There are many students waiting to ask the question.
Okay, ma'am. Sorry.
Thank you.
Now I request Namita Sharma from grade 10 to put forward her question.
Good evening, all the dignitaries, and good morning to George Salazar, sir, as it's morning in Texas. Thank you so much, sir, for the presentation and allowing us to interact with you. I would really like to ask, the question that why is Higgs boson particle, also known as the God particle, so important?
Oh, wow. Okay, so you saw my presentation, kind of a representation of the Higgs boson particle. And actually, I think they discovered that at the CERN particle facility in Switzerland, if I'm not mistaken. But it was an indirect measurement. And so one of the interesting things about this particle is that it suggests that it created a mass from matter. And this is a little bit very challenging from a standpoint of science. And hopefully you'll be the person to discover this, but can you take matter and run it through a Higgs boson particle and create mass out of it? I mean, it's just amazing. You know, it kind of reminds me of invisible energy. Okay, there's invisible energy, and let's say there's a door with this Higgs boson particle beam generator, and then you take this invisible energy, run it through that door, and then all of a sudden you get this mass of a person or a mass of an object. It's just an incredible thing to comprehend and understand. But the importance of this is that apparently this Higgs boson particle is kind of the building block, if you will, of mass, and that's one of the kind of the critical findings of the Higgs boson particle. That's why they call it the God particle, so to speak, because if you think about it, if there was no mass, none of us would be here right now. Nothing would be here. The computer would not be here. You would not be here. Nothing like that. We're mass. You know, we're made out of mass, and so it's this God particle that helped create what we are right now, which is very interesting. Good question.
Now I request Vaidehi Navle from grade 9 to put forward her question.
Good evening, everyone, and good morning, sir. I'm Vaidehi Navle from grade 9, and I aspire to become a scientist. First of all, I'm really glad and delighted to meet you, sir. My question for you is that more than 100 years ago, a very famous and genius scientist, Albert Einstein, suggested that space and time are linked together. He called this relativity. And he also said that our universe has a speed limit and nothing can travel faster than the speed of light. So, taking all into consideration, is time travel possible?
Is time travel possible?
Yes, sir.
It probably is, and so here's the challenge. And maybe this is, I think you say you want to become a scientist, which is fantastic. It'd be a challenge to figure out how can you do that. Of course, we see in the sci-fi movies, that they can travel back into time by going faster than the speed of light. And there's actually something called tachyon emissions that suggests that these particles can go faster than the speed of light. In fact, we're looking at that. NASA's looking at that at a research level for communications, instantaneous communications. That gets into quantum mechanics. So I think it's possible to travel in time. It's easy. The cheap way of traveling into to time going backwards is just going outside and looking into the stars, and you can see time that has passed over the years. But going forward, that'll be interesting. Of course, the question now becomes is philosophical. If we go forward in time, are we going to alter our present time? Am I going to change time? Am I going to change the outlook of my family, the outlook of me? Am I going to change that? These are all philosophical questions that we have to answer. So if we do have the capability of traveling in time, we're going to have to develop a, let's call it a policy of how we're going to behave if we do travel in time. In Star Trek, they talk about not interfering with other cultures and other civilizations. We're going to have that same philosophy. In fact, what theory, it's whatever you want to call it, conspiracy theory or whatever, is that we're being visited by time travelers, but we don't see them because they probably have the policy in place to not disturb the past for them. And so that could be the possibility. But maybe one day you'll be in the front headlines of the newspaper discovering the time machine.
Thank you so much, sir.
You're welcome.
All right. I think Vaishnavi Verma is being raising hands again and again. Your question has already been asked, child, when you did not respond for more than 30 seconds. So your question has already been put to Mr. Salazar and he has already responded. Now, I appreciate and I do understand that children are extremely enthusiastic and they are interested to ask many more questions. But as already informed to all of you that the questions were already selected out of 300, more than 300 questions. And these 20 questions were given a chance to speak to Mr. George Salazar. Mr. George Salazar, I have a request. There are many questions, I think, in the chat box, wherein in a Q&A session, a Q&A option. If you could see that and if you find any question that should be answered, would you like to answer those questions, Mr. Salazar?
I can answer a few, sure. It's just if too many start coming in, I can't I can't keep up.
Okay, I will read some of them. One of the question is, why don't we send some water in some rocket to the planets using a container tank?
Can you repeat?
Reaches Mars, it would be frozen and then we can use it. So what's your say on that?
Okay, so sending water to another planet by freezing it?
Yeah.
Okay, so here's the difficulty of space exploration. I don't know if you've heard the term that weight can be it's expensive to launch weight into space, and so the bigger the object, the bigger the payload, as we call it, the more energy it takes. The more energy it takes means the rocket has to be bigger. That means that it's more expensive. And so the thing about water is that it's very heavy. It weighs, roughly, if you use the standard system, 1 gallon of water is about 8 pounds. Okay, so it's very heavy, and of course, it takes a lot of water to support a human. All right, for 1 year. And so we can only take so much water with us, but the rest we're going to have to learn how to develop methods. That's why in situ resource utilization is a very important technology for going to other planets and learning how to extract water from this land in order for astronauts to live and work in another planet. We just cannot take all the food, we cannot take all the water, we cannot take all the oxygen that's needed for living on a planet for a long period of time. We're going to have to learn how to live and work on another planet.
Okay, this question is again given a beautiful solution. I mean, I think you would be the best person to answer this. The solution given is, after the water reaches Mars, it would be frozen, and then we could use heater to melt up again. Then we can get some algae or trees, like example Tulsi, so they can make oxygen and then it can be habitable. So is it possible?
It's possible, but here again, it's a matter of demonstrating that technology on on the moon first, and because we want to get it right before we take it to Mars. We don't want to, like for example, the example that was given to me one time is, you don't want to build a boat made out of certain material and then test it in a little lake and then take it to the ocean. All right. You want to first obviously test it on the lake, but then slowly test it in bigger and bigger types of water till you get to the point that you're very comfortable testing it in the ocean. And so that technology is possible, but we need to test those capabilities on the moon to see if it's going to be possible on Mars.
Okay. One question from Master Om Gadekar is, has the mankind grown such an intellect and he or she can wrap time?
Can you repeat that again, please?
Has the mankind grown such an intellect that she can wrap time? Even I'm not very clear about this question. I'll move it to Ishan Malbari, who's asking, what is the fact behind the sentence, Mars has the biggest volcano in the solar system?
Yeah, Mars does have the biggest volcano in the solar system. That's something we're going to have to explore one day and see what's there. So if it's a volcano, then how did that volcano come to be? Well, we know here on Earth, volcanoes are built up from molten lava. So what does that mean? Well, there's molten lava. That means that we have a mantle, or if you think about the Earth, there's a mantle system, and it's got a core, right? So that core is rotating in a fashion that creates an electric field, electricity current, which creates a magnetic field. And so we need to study that volcano to see how it came to be. If it was because of the Mars center core was similar to Earth, that means that the Mars once had a very strong magnetic field. If it has a very strong magnetic field, it protects life from radiation, what we call galactic radiation and solar radiation. So that means that life one time flourished on Mars. Well, what happened? And that's what we need to study. So that volcano is a very good example of going there and taking instruments and studying it to see how was it built and why did it's no longer active. That's a good question.
Okay, thank you. I have another question from Vaishnavi Verma. Sometimes the astronauts find something defective in the rocket, then how do they come back?
Oh, wow. So if something's defective, it got past us during all the testing. It's just incredible the amount of testing that we do before we launch a rocket, because we got to get it right the first time. There's no oh, I forgot this or that. We have to test it, test and test again to make sure that everything is working properly. When we get into orbit, they're constantly testing out all the systems. If something breaks, it depends on what breaks. They might be able to repair it. But that's why we built what we call redundancy into spaceships. What is redundancy? Redundancy means that we have backups systems in case the first system fails. Like, for example, on Space Shuttle, it had 3 battery systems. So, 2 battery systems could fail and we could still bring the Space Shuttle home. So we have to build redundancy in there. And that redundancy can get expensive. It can get expensive in terms of cost. It can get expensive in terms of weight, because you're adding weight to the vehicle. Remember what I said, the more weight, the more expensive it is to take it into orbit. So we got to be careful how much we design. We can over design a system and it gets so heavy and so big, it can't even take off from Earth. So it's a balancing that we have to do in engineering to figure out how much redundancy we put into the system, so that way, in the event something breaks, it's okay. They can still come home. But if everything breaks, they got a very bad day. And of course, I can give you one example that of the Apollo 13. That was a bad day, where that hydrogen explosion took out all their oxygen, and they had to go live and they had to crawl into the lunar module and live there for a period of time until they got home. Hello? Oh. Okay, I've lost the audio.
Hello, can you hear me?
Hina madam had,
Yes, can you hear me, sir?
I can hear you now.
Okay, I was saying,
Lovely madam, I think Hina madam is having something network issue. You can read some of the good questions from the question and answer. Yeah.
One of the questions is, can we say that black holes are a door to a parallel universe? Am I audible?
Yes, you are.
Hello, can you hear me?
Yes, sir.
Okay. I'm sorry. I had an internet hiccup here.
I'll repeat the question. The question says, can we say that black holes are a door to parallel universe? Sir, I think you're on mute.
Okay. Can you hear me now?
Yes, sir.
All right. Sorry about that. So black holes going into a black hole could be a travel in time in in some respects. We don't know that. I mean, that's the theory that potentially black holes are, sometimes they're called wormholes into other universes. But we won't know until we build probes that can actually survive going into a black hole. And then secondly, how do you transmit information back that went into a black hole? Since theoretically nothing escapes a black hole, what do we do? How do we do that? And that's a major scientific and engineering undertaking. And I'm hoping that some of the students there, a lot of smart students, just by the questions that they ask, will be able to solve that problem.
Shall I ask the next question?
Hello, Amol sir, can you hear me? Hello?
Yes, ma'am, you're audible.
Okay, I think Mr. George.
I'm back.
Oh, yeah, oh, yes, you're welcome back, Mr. George. I think you have. Yeah, even I had connectivity issue. We will take last two questions, and then we will definitely, close this session.
Sure.
All right. Okay. Lovely madam, if you could read last two good questions for Mr. Salazar.
Sure, ma'am. One of the questions is NASA researching on a new planet where humans can live?
Yeah, it's a good question. I mean, right now we're looking at the discovery from Kepler, the almost 3,000 exoplanets that are out there. One of the challenges is the distance that a lot of these planets are located. I mean, they're millions of light years away from us, and traveling in space, it just takes a long time. I'm going to give you an example. Voyager spacecraft left our solar system just recently. It took it almost 41 years to leave our solar system. I was traveling at 35,000 miles per hour. But even at that speed, because of the distance, just to leave the solar system took 41 years. So imagine trying to go from one solar system to another solar system. It takes hundreds of years. And so at this point in time, the best we can do for near term is to go to Mars. And that's a challenge in itself. So Mars is going to be our, let's call it the dress rehearsal, for the lack of a better term, of going to other planets and other solar systems. But we need to learn how to live independent of Earth. And that's why going to Mars is what they're calling Earth independent missions, because we cannot depend on Earth to help astronauts as easily because we're so far away. So that's a good question.
Thank you, lovely madam. I think
Hina madam.
Bipin Pote, sir. Hello.
Hina madam.
Yes, Bipin sir, last
Yeah,
question, we will take it from your end.
Yes, please.
Yeah,
Mr.
sure,
Thank
sure.
you very much. Yeah. My last question is: how did the SpaceX make launch cheaper than NASA? They had that 50% amount. SpaceX had the launch cheaper than
Okay, I'm hearing.
how did
I'm hearing two voices.
Your voice is
you are
sir.
hearing
Your voice is
Am I audible?
Okay. Let's
How did
see.
the SpaceX make the launch cheaper than NASA?
Oh boy, your audio is breaking up.
Hina madam, am I audible?
Oh, all right. Maybe can you type the answer?
Yeah. Okay. Fine. I'll type the question.
What? Try to. Oh, you're typing. Okay.
Lovely madam, am I audible?
Okay. I see a question. NASA is working on a satellite that can observe the sun clearly. Was that the question? Yeah.
No, sir.
Lovely madam, can you read the question?
So I haven't received the question, sir.
I see some questions in the question and answer box. Is it in here or? The audio just seems to be getting bad. I don't know.
Yeah,
please check the chat box, lovely madam.
Yes, sir. The question is, how did SpaceX make the launch cheaper than NASA?
All right. So this is boy, this is a interesting question. So here's the thing. SpaceX, you give them a lot of credit for doing how they do their space program, but they used a lot of NASA's technology and knowledge to develop their SpaceX rocket, and also I have to say that Yeah, they did it cheaper because of the tools that they use, the development tools, and how they develop their systems. So they made it cheaper by by using a lot of technology that used properly can provide cost savings in developing rockets. NASA, when it developed its earlier rocket systems, Gemini, Mercury, Shuttle, all this, we didn't have the kind of technology and the kind of computers that they have now. I mean, now you can model, three-dimension systems, and you can get a lot of data out of that. And they use that very well. They got very smart people using high-tech technology tools for doing that. So to answer the question is they use very sophisticated tools, and they know how to use those tools very well.
Okay. Thank you, Mr. George. Yeah.
You're welcome.
Hello, am I audible?
Yes, I can still hear you.
Okay. All right. Thank you, Mr. Salazar. I think our last question also, I mean, I don't know whether Bipin sir was able to ask it.
Yeah, Hina madam had asked already question. Lovely madam had read on behalf of me.
Okay. Thank you so
Yeah,
much.
Mr. George, March 30 VR program is going to launch at March 30 VR program. March 30.
I'm sorry, can you repeat that, please? You kind of broke up.
Mars 30 program, sir is asking about. Has it been launched?
The Mars
30 program.
Boy, I'm having difficulty with audio here. I don't know what's going on. I heard program.
Question being launched.
Hello, am I audible?
Hello.
Lovely madam, could you
I
read
can hear you.
Thank you. Lovely madam, could you read the question to him?
Sure, ma'am. The question is the Mars 30 VR program launched?
March 2020?
Mars 30, 30.
Mars 2030. Is that what I heard?
No, okay. That's fine, no problem.
It's all right. All right, Mr. George Salazar, you have been very patient with the students, and you definitely answered a great number of questions of all these students. Thank you so much for being there with us. And all the panelists, students, and parents, I would also like to say that Mr. George Salazar is a senior life IEEE member, a registered professional engineer in the state of Texas, and an expert systems engineer professional certification through the International Council on Systems Engineering. He enjoys sharing knowledge with students that we have witnessed is very fruitfully. He is also the co-founder of Human System Integration, HSI, Employee Resource Group, with the goal of infusing HSI into NASA technical processes. Thank you, Mr. George Salazar, for being with us. As the culture of our organization, we always conduct a vote of thanks. Now I request Ms. Varsha Sharma to please give away the vote of thanks to conclude this program. Over to Ms. Varsha Sharma. I hope I was audible. Thank you so much.
Thank you, Hina ma'am. Good evening, all of you. Ma'am, am I audible? Lovely ma'am, am I audible?
Yes, Varsha,
yes, you are audible.
Thank you. Good evening, one and all present here. Myself Varsha Sharma, and it gives me immense pleasure to propose the vote of thanks for this wonderful event. First and foremost, I would like to thank the inspiring and motivational speaker of the day, Mr. George Salazar, sir, for blessing all our learners by his knowledge and encouragement. Now, I would like to thank the person who defines leadership, our very own respected mentor, CMD of Pote Group of Education, Mr. Bipin Pote, sir. Thank you so much, sir, for providing us with this once in a lifetime opportunity. Now, I would like to thank our dearest, beloved, inspiring managing trustee, Mrs. Minal Pote, ma'am. Thank you so much, ma'am, for providing us with this amazing platform of learning. Now, moving forward, I would like to thank our dearest principal of school, Mrs. Hina Falke, ma'am. Thank you, Mrs. Hina Falke, ma'am. Thank you so much, ma'am. Without you, this event would never become so grand. Now, I would like to thank our pre-K head coordinator, Mrs. Sabita Rao, ma'am, for her support. I would like to proceed with thanking our very own IT head, Mr. Amol Shinde, sir, for his hard work in making this event a success. I would now like to thank all my heads and my entire TCS family. Each one of you has worked really hard in making this event a success. I would now proceed to thank all my lovely learners and my supporting parents for their active participation and support. Last but not the least, I would now like to thank our media guests for their presence in the event. Thank you so much, all of you, once again. Have a good night. Thank you so much. Stay safe, keep inspiring, keep growing. Thank you.